Hi guys, welcome back to yet another video. This is Madhu Kashyap. Today we are going to talk about relativistic quantum mechanics. I know this is a very exciting topic and a higher topic. So let's kick on with it. Relativistic quantum mechanics. We start with something called as Klein-Gordon equation. In short, we can call it as KG equation. Okay, so we start with this. Why do we use this? Because we use it for spinless particles. Uh, we need to understand the spinless particles. Uh, for example, like pi mesons. All right. So we are gonna start with pi mesons. Or like the spinless particle, we can take that as an example. Um, Now let's start deriving this expression. So how do we derive this? We take all our natural unit systems, our natural unit system, which is our Planck's constant h cross, which is h by 2 pi, and the speed of light c. We put all the constants equal to 1. Just to make our calculation simpler, we are going to do this. Now we start our derivation with using Schrodinger equation. Okay, so we take the kinetic energy part of it, h cross minus h cross squared by 2m, del squared psi plus the potential part v psi is equal to e psi. We just said h cross is equal to 1, right? So minus 1 by 2m del squared psi plus the potential v psi will be equal to E psi. So this is the Schrodinger equation part. Okay. Now we are gonna take the now we took the quantum mechanics part. Now we will look at the relativistic energy part. Einstein's relativistic energy part. We know energy equal to mc squared. So basically we are taking the energy momentum relationship now. E is equal to p squared c squared plus m squared c power 4. In the previous slide, we said h cross is equal to c is equal to 1. So we are going to put speed of light is equal to 1 here. So e squared is equal to p squared plus m squared, right? And we know we will apply some operators to make it much more simplified version of it. Energy operator for this would be equal to, I can just put a mark like this, which will be I h cross dou by dou t, and the momentum would be minus I h cross del, right? Since here we put h cross as 1, the energy would be just I dou by dou t. Okay, I think, okay. And the momentum part would be minus I del, right? So this is how, and this equation, if I put the operators in the place of E as I, which would be I dou by dou t. Okay, let me just take the eraser. Where do I find the eraser? Okay, and I dou by dou t the whole square, right? Which will be equal to minus I del squared plus m squared, right? So this is the energy expression we got. And now if you compare this expression with our previous, we can call this as equation 1. for simplicity's sake, and we can call this as equation 2. Now what happens when we combine both the expressions? What do we get? We will get, okay, which would be minus dou squared by dou t squared minus del square plus m square into psi will be equal to 0. This is basically the kg equation. You can write it as dou mu dou power mu plus m square into psi is equal to 0. This is another way of writing it. It's just writing in different format. So this is basically your Klein-Gordon equation. So this is actually used as spinless particle, and it is also used in our Large Hadron Collider. So this is very important and fun expression to learn to understand the relationship between relativity and quantum mechanics. We can do much more detailed work. If you want videos like this, kindly leave a comment below and we can discuss more and in detail. I just want to see how many curious minds are interested in learning this kind of advanced physics. Okay, see you in the next video. Thank you very much. Have a nice day.